Hello there. I've been taking a small break from posting videos, but thanks to all your wonderful reminders, we are back on track. In our last episode, we had generated the image of a sphere. However, it looked more like a flat circle. This was because our model was a bit simplistic. If a ray hits an object, then we ask that object's color, and that pixel becomes that color. If it does not, then it's black. This is a bit like a blind superhero prodding what he thinks is a giant inflated ball, but it's actually Kingpin. This daredevil approach, pun intended, would likely to give you only shapes with flat colors. No shading, no shiny or dark spots, just uniform color. So let's try some more shady, pun intended again, techniques. Our model lacks a crucial element, light. As experienced photographers know, lighting can make all the difference. So let's introduce light. Problem solved? Actually, no. Light can bounce off objects, reflect, refract, and do a million other things while it is dancing all over your scene. But we can significantly improve our model by just focusing on three components of how light bounces off objects: ambient, diffuse, and specular reflectivity. This is commonly known as the Phong model, or as I like to call it, the three bears. Ambient, the little bear, is actually the faint overall light in the scene. This is why shadows in real life are not pure black. In fact, if you enter a dark room and if you give your eyes enough time, you can see some faint outline of the objects in the dark room, even if there is no light source. This is because thanks to ambient light. Diffuse, the middle bear, is when light hits a rough or matte surface like wood or paper, when light scatters or diffuses in different directions equally. Actually, all materials exhibit diffuse reflection, unless it's a perfectly reflective surface like a mirror. Specular, the big bear, is that shiny spot of light which is reflecting off a smooth surface. This is commonly observed in materials like marble or metals. Again, most materials or objects show specular reflectivity. If all this sounds very confusing, then please bear with me, pun again intended. I will explain this in detail soon. According to the game engine architecture book, the Phong lighting model is the most common local rendering lighting model used by game engines. So if you implement this model, your images will look way more 3D. So let's dive straight into it. Now let's look at what are the requirements for subproblem number 4 involving light. The requirement is quite simple. We have to apply the various shading algorithms to the ball. First, let's look at what is diffuse shading. Diffuse shading is basically very prominent if you look at a matte surface, or in simple words, a rough surface. Something that is not very reflective, something that is not very shiny. So if you look at the ball on the screen over here, you can see that it's not completely of a flat color. The middle part is a little more brighter than the edges. This is known as diffuse shading. It is because the light gets diffused. It's not shining back to you like a mirror. Because it's a rough surface, it is diffused by that material. So there are various shading models for diffuse surface, and the most popular would be the Lambert shading model. Now, if you look at the picture on the right over here, the first picture that I would like you to highlight on is basically a square beam of light. A beam of light is falling on a red surface. This beam of light is square in shape, so even though it might look like a parallelogram or slightly skewed square, it's basically a square of light which is falling, a square of yellow light which is falling on a red surface. Now we call this 0 degrees because it makes, if you look at the normal of the surface which is pointing straight up, the light and this normal is making 0 degrees. There is no angle between them, it is 0 degrees. So what I basically mean to say is that the light is falling directly perpendicular to the surface. So this is the 0 degree situation, and you can see that if we draw a similar square on the surface, all of the light energy is falling on that square. So this means that entire light energy is perfectly falling on the square. The next figure on the right is the 45 degree scenario. So the light got tilted by 45 degrees to the normal of the surface, and the square beam is no longer contained within the square drawn on the surface. The light gets spread. In other words, the light energy is not fully captured by this square surface. So only a part, I would say a significantly less part compared to the first example, is now falling on this surface now. Now let's look at the other extreme example, that is a third picture on the right here. This is a 90, this means that the light is making a 90 degree to the surface. In other words, the light is not even touching the surface, it is just grazing through the surface, which means that none of the light energy falls on the surface. So we started with all of the light energy and we end with none of the light energy falls from a 0 degree situation to a 90 degree situation. So this is perfectly captured by a trigonometric function called cosine. If you remember from your mathematics classes, cosine is a function which gives you almost entirely, which returns 1 if you give 0 degrees. So cosine of 0 is 1, and if you give it 90 degrees, cosine of 90 is actually 0. So cosine is the perfect example, is the perfect function which can capture this loss of energy, or this how much light energy is captured based on the angle of incidence. So I'll just read out the cosine law for you. When the light falls obliquely on a surface, the illumination of the surface is directly proportional to the cosine of the angle theta between the direction of the incident light and the surface normal. In simple words, when light falls on a surface, you just have to calculate the angle on of the light falling, and between the normal of the surface and the light falling, we call it theta over here, as you can see in the diagram at the below. The theta is the angle which is made between the normal and the light, and the amount of light which is falling is directly proportional to, or in other words, you can find out how much light is falling by finding cos theta. Now, in case you're wondering, we are actually dealing with vectors here. So the normal is a vector, the light falling is a vector. There is no need to calculate cosine because we already have another function which is called dot product. Now, why are we talking about dot product? There is a relationship between dot product and cosine. The cosine of the angle between two normalized vectors, so remember it is normalized vectors, the vectors must have a magnitude of 1 as we discussed in the first episode, is the dot product. For example, cos theta equals L dot n. So since we already have a way to calculate dot product, instead of calculating cosine, all we have to do is calculate the dot product. So how does our modified Lambert shading model look now? So the diffuse color on a surface, the color of the surface here refers to the diffuse color, is equal to L dot n. L is the light vector, n is the normal vector, multiplied by m diffuse, multiplied by color of object. So these are the terms here. L is the ray of light, n is the normal at the where the ray of light is hitting you, m is the material's diffuse coefficient. So even though this might sound like a technical term, all it means is how much of the material absorbs this diffuse coefficient and how much you can see. So if I put m equals 0.5, it means that you can only see this effect in a 0.5 way. If I make it 1, it means that this coefficient doesn't matter. Basically, it's a very rough surface, so you can see the full effect of Lambert shading model. If m is a very small value or closer to 0, that means it's not a very rough surface, it's a smooth surface. So the Lambert shading models, or in other words, the diffuse effect is very minimal. You're not seeing much of diffuse effect. So that coefficient is to adjust based on the material on which this light is falling. And finally, we have the color of the object, because all these terms will multiply and give you a single value. It's not a vector value, and that will be applied to the color of the object, which is a vector value, and the color will be either seen very brightly if the number is 1 or more than 1, or it will be shown in a diminished way if the result is less than 1. So one thing to remember here is the dot product result here should not be negative, which is not much of a because if you multiply a negative number with a color, which actually removes that color from the final object. So remember, this diffuse coefficient is actually a component that we'll add to our final color. So we are basically mixing colors here, we are adding colors here. So we don't want a negative color, so that we subtract colors here. So make sure that the dot product result is not negative. There's not much of a problem in the Lambert shading model, but it'll be in the next, we'll soon see where it will be a problem. Next is specular shading. Specular shading is basically the reflections from shiny plastics or any shiny surface. A plastic is just one example. And you'll see a faint outline of how specular looks like in a picture of the image on the right. So the ball picture over here has a small shiny spot which is the light source. If it was the sun is reflecting on that ball in a very shiny way. So as you can imagine, if it was a very rough surface, it would not have these shiny spots, and the specular shading effect will be diminished. What we are going to talk here is something called the Blin-Phong shading model. Before we talk about Blin, let's look at the simple Phong shading model, which is the initial model in which this was calculated. So we all remember how mirrors work, right? So mirrors basically reflect light, and the formula for a mirror is very basic. The angle of incidence equals the angle of reflection, right? So that's what the image over on the right shows here. If you draw a vector, if there is a light source which is falling on a surface, this red surface, this line of incidence should makes an angle with the normal theta. And if you want to see where the reflected light goes, it will be exactly making an angle theta in the opposite direction, right? So light came from the light source, hit the material, and reflected off as R, making an angle of theta, the exact same angle with N. Now, the person who is looking at this object might not be standing at R, right? That's drawn at a different position over here called V. Now V is making a different angle, and with the normal with R, and it is the angle between V and R that matters, and that is why the Phong term is V dot R to the power of S. So if you are standing exactly at the position where the reflected light would have been, imagine if it was a mirror and you're standing where the reflected light is, you'll actually see the light source in full intensity. It'll be literally shining back to your eyes. Now, if you step a little away from R, the intensity of light which is shining back to you will reduce. So that means that is what's meant by this dot product. Now, if you are very far from R, it will be very diminished. So basically, Phong shading model, I'm just reading it out here. Right, light reflected varies based on the angle difference between the view direction and the direction of perfect reflection. So the view direction is V and the direction of perfect reflection is R. And there is something called a Phong shading coefficient that is used to adjust how much strongly the reflection happens, and that is called S here, and the whole term is raised to the power of S. As you can see here, I have written this formula: Phong term equals V dot R to the power K, where I've just modified that S to K here. So V, as I said, is the ray towards the viewer, towards your eye. R is a light ray reflected direction, and K is a specular coefficient or shininess. This is similar to our diffuse coefficient that we learned earlier, except that it's now a power. There is one issue with the Phong shading model, that is that the angle between V and R can be larger than 90 degrees and the dot product can be negative. So just to go back here, if you see that the person who is looking and the angle of reflected R could become any angle from 0 to 180 degrees, right? The person standing over on the right would actually move to the left, and this angle could be very high, which is perfectly fine in the real world. But if you are calculating a dot product or a cosine, this means that the angle will become more than 90 degrees and the term will become negative, which we don't want. Hence, we have a modification called the Phong blend modification, which calculates something called a halfway vector. So halfway vector is the angle which is halfway between the viewer and the light source. Basically halfway between the larger angle made between V and L is cut into half. So you can see that if you go from L to V, at halfway you will see H in green color. So how do we calculate the halfway vector? In vector mathematics, what we do is just we add L and V. So if it was L and V over here, if you shift V to the position of L, it will actually be L plus V, and it will be in the halfway position between L and V. And remember, H has to be a normalized vector, so a further modification is done and we normalize H. Now instead of V and R, the blend term is actually H dot R to the power of S. And again I replaced it with K over here. So blend term is now H, halfway angle between the view and light sources, dot product R, which is a reflected direction, and K's specular coefficient. So what happens when we combine diffuse and specular shading? So the sphere on the top, or the circle on the top, was our previous image that we created using in episode 3, which is basically a flat shaded circle, and the image below is the effect of combining diffuse and specular shading. As you can see, it's almost like a 2D image became a 3D image, which with nice shiny lights and nice shading on top of it. So these components, the diffuse and specular components, are critical and pretty much what sells the effect of a 3D object, if you're making a 3D object. Now, before I tell you to go ahead and implement this, you might need to understand, or you might need certain hints that will help you in implementing a solution. So you might have noticed that I keep on talking about the material, and we do not have any data structure for storing the material so far till episode 3. So I suggest that you create a data structure for storing the material, in this case the red colored ball. and what are the components, or what should be inside this data structure. One thing you should probably have is the base color, which is red in this case, so it's a red ball. So we store something called color, which is actually the base color. And the second thing we need is ambient. So even if there is no light source, there is an ambient light which is falling on the object, and what color is it, how much is it in intensity, is what is known as the ambient component. That's the second component I would recommend. The third component I would recommend is diffuse component. We already saw that in Lambert shading model, what color it reflects in diffuse light, or how much it reflects in diffuse light. In fact, it should be more of how much than the color. Specular component. So what is the color of the specular highlight, or how much specular highlighting is there? Basically how much shininess is there. If diffuse is how much roughness is there, specular is how much shininess is there. Continuing the implementation hints, I would also suggest that you have a light source. Light source is basically quite simple. You can say where the light is and what color it emits. So in my implementation, I'll probably not use the color. I'll assume that it is white color, but no, I think I'll use a default of white color, but I'll also use the color, because color is also important when it comes to the source, or how much, what kind of color is coming out of it. As always, we have some bonus points for better implementation. So in this implementation, I would like you to think about how you can change the command line, or in every time we run our program, it's actually creating a file called test.ppm. Now I want you to mention what output it needs to create. I don't want you to hard code where the location of the test file, or where the output is. For example, I want to output it into a different name. I want to call it image.ppm. How do you change that? I don't want you to change the code. I'd rather like you to mention what is the output file in the command line itself. This is basically a good command line interface, or a good etiquette maintained by command line programs. So if you can mention that as a command line argument, that is a bonus point. Another bonus point, if there is a word like that, is can you show some progress indicator? When we run our programs, it's actually going to take a lot of time, because it's ray tracing is going to be slow. How can we see that there is something happening? So you can either show a progress bar, or you can just show a number which shows 0%, 10%, 100%, like that. So some sort of progress indicator would also give you bonus points. Alright, so as before, please pause this video and try to do this code yourself. Try to think how would you actually go about implementing based on whatever requirements that I've told you so far. And if you're able to create some code which is working, or even if it is not working, it is going to significantly help you in understanding how my implementation compares to yours, or in helping you understand better how we can actually implement a ray tracer. So go ahead, pause, and I'll see you on the other side of this break. So welcome back. Now I'm going to start with the main program. So main program does not have two things that we talked about, lights and materials. So let's fix that. So let me add some lights. And I'm assuming that there is a thing called light, which I'm going to create in a minute, but assume that it has a point position, and I'm just going to give a position here which I have checked after some trial and error. So it is 1.5, minus 0.5, and minus 10. and color from hex would be white. So that is ff the hash ff, right. So we need to define that light, so I'm assuming there is something called from light import light. So let's create that light.py class light. So I'm going to give a small doc string. Light represents a point light source of a certain color. Now the initial constructor would ask for the color and the position. So if the color is not given, let's assume it is white as before, ff. So it import color, and self dot position equals position, self dot color equals color. I think that's pretty much it. Next we need to import that. We have imported that camera objects lights. Next is material. I'm assuming that, so our sphere over here used a color from hex as material. I'm going to change it to material, and I'm going to import that from material, import material. Class material has color and properties which tells us how it reacts to light. Okay. Self should have some color equals color from hex. So what color would you like to give? Let's give again white. From color import color. What next? Ambient, a very faint ambient, because ambient light is faint light. Diffuse equals 1, because diffuse is the most common. Specular equals 1. Okay, self dot color equals color, self dot ambient equals ambient, self dot diffuse equals diffuse, self dot specular equals specular. Now we are mostly done with what we need. We have a material which is red color, and then we have the rendering scene. Next we need to go to the engine. So our engine so far has a ray trace function which calls color at, and that's it. So it's somewhere here that we need to calculate the diffuse and specular. So before that we need to calculate what is the normal at the hit position, right? So I'll call this as hit normal. It's equal to object hit dot normal at hit position, right? So we're going to pass that self dot color at hit normal. Now all our objects are spheres, so let's create that normal for a sphere. Self, I'll call it surface point returns surface normal to the point on sphere's surface. So it's very easy to calculate the surface normal of a sphere. That's the reason why we are using spheres in ray tracing. All we need to do is calculate the difference between the surface point and the center of the sphere and normalize it. So return surface point minus self dot center, put a bracket around it, dot normalize. Okay, that looks good. Next we go back to our engine. So this is primarily where we are going to make all our changes color at. We have the material now. So we're starting with the ambient color. The only thing we don't have is the base color, which is color at. So we'll go to material again. Hit position. That's the direction and the position of the light. I think we forgot to mention normal over here. Color at is called with object hit position, hit normal and scene. Object hit position, normal and scene. Okay. Now to specular shading. So just to give you a quick overview, we are going to use max here because sometimes normal can be negative despite all our safeguards. So I'm going to make sure that it's either 0 or greater than 0 by using this max function, and same way I have done for here. So I forgot adding lights. Okay, now the remaining is the bonus. So let's look at how we can add arguments to this. So argparse is a very common argument parsing library. It starts with argparse, not argument parser. This is a lot of options. You must call parse args so that it gets parsed. Now we'll replace this hard-coded test.ppm with args.image out. Let's see how that works. So it says that there is an image argument required. Can say out.ppm. Comes out feh out.ppm. There you go. You have the rendered results. The final bonus is to create a progress bar. So let's try that. So I'm going back to the engine. There is a place where the rendering happens line by line. So I'm going to add a print statement over here, which just displays the percentage. So I'm going to say something is getting printed in percentage dot format. Now I want to divide how many rows have been rendered so far, but I have to divide it, so I want it in floating point. Float of j divided by float of height, and I want it as a percentage, so it should be into 100. And Here's the string to show it in a certain width. So it should be :3.0f. Okay. So ideally I would like it all to come on the same line. So I'm going to say end /r. It's a common trick which is used in progress bars. Wow, look at that. Let's try that again. Awesome, right? Now let's see. There you have it. So hope you enjoyed this. Thank you very much. Did you like this video? Then please share it with others. Comment about how you feel. Most importantly, subscribe and press the notification bell so that you get to know about future episodes more quickly.